All right, let's get started. Welcome to the cryptanalysis session. Our first talk is ML-based cryptanalysis inherently limited, simulating cryptographic adversaries via gradient descent methods by Avital Shafran, Aaron Malach, Thomas Ristenpart, Gil Segev, Stefano Tesaro, and Avital is giving talk.
Thank you for the introduction. Hi everyone, my name is Avital, and I will be presenting our work on machine learning-based cryptanalysis. As you mentioned, this is the joint work with Aaron Malach, Thomas Ristenpart, and Stefano Tesaro. So I'm sure I don't need to say this in this room, but as you all know, cryptanalysis is going to be labor-intensive and complex process that requires a lot of creativity. Given the fact that machine learning has revolutionized many manual tasks in the past decade or so, such as autonomous driving, anomaly detection, language translation, it only made sense for researchers to start asking whether they can use these recent ML methods to also replace some of those classical labor-intensive cryptanalytic approaches. And there's been some previous work about this, mostly focused around attacking block ciphers and the LWE problem. Most notably is the work of Gore from Crypto19 that presented the first neural distinguisher for attacking the spec block cipher. This work had many co-mods and extensions to other block ciphers as well. Another notable work is the work of Wenger, Chen, Sharpen, and Lauter from New York's 2022 that presented SALSA, where they used machine learning to attack the LWE problem. The methodology behind many of these work is as follows. They first collect a large sample set, they use that to train some neural network, and then they challenge this neural network with some corresponding tasks. So in the case of Gore, the sample set is composed of ciphertext pairs with either fixed input difference or random input difference, and the task would be a distinguishing task between these two types of pairs. In the case of Wenger et al., the sample set is composed of LWE pairs, and the task would be secret recovery. In our work, we're actually motivated by the key difference where in the way the different methods access the underlying data. So while in classical cryptanalysis, we directly process individual samples, such as plaintext, ciphertext pairs. But in machine learning, we do not do that, and we actually indirectly process the samples using gradient-based computations that are averaged across multiple samples. And this difference in the way that we access the underlying data motivated our main research question, which is whether these machine learning-based cryptanalytic approaches are inherently limited due to their more restricted access to the underlying data. If the answer to this question would be no, it means that any sample-based classical cryptanalytic adversary can be simulated by a gradient-based machine learning adversary. Well, if the answer would be yes, it means that there exists some sample-based adversaries that cannot be simulated by those gradient-based adversaries. Our contributions include the introduction of the unifying framework that captures both those sample-based adversaries and the seemingly restricted gradient-based adversaries. And we use this to obtain a general feasibility result that does state that any sample-based adversary can be simulated by a gradient-based adversary. For showing this, we present in the paper a series of simulations with increasing level of restrictions. And interestingly, we also observed that in all of our results, we did not observe any significant loss in efficiency, where efficiency is measured by the query complexity and the runtime of the gradient-based adversary. So in the remainder of the talk, I will be presenting our framework, and I will briefly go over some of our results, one of them with a bit more detail, the other two in a more high-level fashion. So in our framework, we want to capture two types of adversaries, the sample-based adversaries and the gradient-based adversaries. The sample-based adversary, exactly as we said, gets direct access to the sample set, can perform arbitrary computations, and output some value. And this captures a wide range of fundamental cryptographic applications. So think, for example, of the sample set as composed of input-output pairs of some key function. Then the output could be a new pair for an unpredictability task, or it can be a key for a key recovery task, or basically any game-based application. For the gradient-based adversaries, we first need to define some machine learning notations. So in machine learning, we have a learner that tries to estimate some mapping between an input space and an output space. And for modeling the common ML methodology, we introduce the notion of a gradient oracle. This oracle gets as input the sample set, a loss function, a parameterized model function, and a set of parameters. and outputs a gradient vector. A gradient vector is a vector of partial derivatives with respect to each one of the parameters. And specifically, in this case, it would be the gradient of the composition between the loss function and the model function averaged across all the samples in the sample set. And basically, the model function and the parameters represent the learner's current estimate of the mapping, while the loss function is measuring the accuracy of this mapping, and the learner usually uses the value of the gradient in order to improve its estimate in the sense that it minimizes the loss function. So for this, we require that the loss function and the model function would be both differentiable, and we also assume that their derivation and computation can be done in polynomial time. So a gradient-based adversary does no longer have direct access to the samples, but rather has some oracle access to the gradient oracle. It can issue whatever queries it wants and perform arbitrary computations. And while this notion of an adversary is already very strong, we also discuss a more restricted setting, but an interesting subcategory of this adversary, which is the gradient descent adversary. So in the common methodology in machine learning, a learner does not perform arbitrary queries to the gradient oracle, but rather it follows a particular iterative algorithm known as gradient descent. In this algorithm, the learner first fixes an initial query, which is a triplet of loss function, model function, and parameters, and where the model function and the loss function usually remain fixed. And then for a number of iterations, it issues this gradient query to the oracle, gets us output the gradient vector, and uses that to update the parameters following a specific update rule, where basically we take the previous set of parameters, we subtract from that the gradient vector, multiply by some parameter eta, which is known as the step size or the learning rate. So we iteratively update our parameters using the value of the gradient, and the step size determines the size of those updates. As an output, we can do some post-processing over the parameters, output them as they are, the model function, or anything else. So interestingly, our vocal framework and our results also apply and can be easily adapted to other types of learning algorithms. So while gradient descent is known as like the base or the vanilla learning algorithm, it also has many interesting and popular variants, including SGD, stochastic gradient descent, where the gradient vector is averaged across a randomly sampled subset of the samples. Sorry. Is this working now?
Yeah,
Should I start again? Okay, so I hope you managed to hear what I was saying so far. So we have these two classes of adversaries, and in order to be able to compare the two, we need to define some notion of simulation. And we naturally define our notion of simulation as being the statistical distance between the input-output distribution of the sample-based adversary and the input-output distribution of the gradient-based adversary. And we would say that the gradient-based adversary is epsilon simulating some sample-based adversary if for any distribution over the input-output domain, the statistical distance between the two distributions is lower than some epsilon. In fact, in our results, we actually prove a stronger notion of a universal gradient-based adversary that black box epsilon simulates every sample-based adversary. So here, the computation performed by the gradient-based adversary does not depend on the computation that is performed by the sample-based adversary, and we'll see that it has some oracle access to that adversary. In some of our results, we obtain epsilon of 0, which we denote as a perfect simulation, while in other cases, we have a statistical simulation, and in that case, the running time would be dependent on a factor of 1 over epsilon. So let's see how do we actually obtain our results. So our approach is to construct a black box gradient-based adversary that will epsilon simulate any sample-based adversary following the following this methodology, where we first issue a series of specifically tailored gradient queries to the oracle. And again, it's important to note that this is the only degree of freedom we have, choosing this triplet of model function, loss function, and parameters. And we choose them such that using the gradient vectors that we get as response, we can extract a local copy of the sample set, and then we can internally run whatever computation that was performed by the sample-based adversary on our local copy of the sample set. And before I move to the actual construction, I would mention that some of our simulations are inspired by existing work from the ML theory community that focused on learning the power and limitation of differential-based learning.
So our first result is a perfect simulation using DFS-based extraction. And here we present a black box gradient-based adversary that perfectly simulates any sample-based adversary. And interestingly, the query complexity and correspondingly the runtime are linearly in the size of the sample set, which is basically the best we can hope for extracting the entire sample set. And here the idea would be to run a DFS-based exploration to extract all samples, where we will go over all possible prefixes. And if we reach a prefix that uniquely matches some sample, then we will extract this sample. Before I move to the actual construction, I will mention that for the remainder of the talk, I will assume that the input domain is composed of n-bit strings and the output domain is binary. But in the full version of the paper, we also extend this to the multi-bit version as well. So how do we actually construct our queries? So given a prefix z, we want to be able to construct a query, which is again a triplet of model function, loss function, and parameters, such that it will enable us to distinguish between three cases. The case where no sample matches the prefix, the case where exactly one sample matches the prefix, and the case where multiple samples matches the prefix. So that starting from an empty prefix, if we reach one that does not match any sample, then we will terminate this path. If we reach a prefix that matches a single sample, then we will extract the sample and then terminate the path. And if we reach a prefix that matches multiple samples, then we will recursively invoke the exploration using extended versions of this prefix. So, let's jump. So the gradient, so how do we construct the query? So the gradient vector is the gradient of the composition between the model function and the loss function, average across all samples. And using the chain rule, we can think about this as the multiplication between the derivative of the loss function and the gradient of the model function. And basically, we want to construct, okay, this was supposed to be there, so pretend like it was there. We want to construct the loss function such that its derivative will enable us to extract y, and to construct the model function such that its gradient will enable us to construct x, and it will also enable us to count the number of matching samples. So how do we actually do this? Oh, I'm so sorry. I don't know why it's overlapping. So I will just say this, and I hope you can believe me. So we construct the loss function such that its derivative would be 2 plus y. I remind you that y is binary, so 2 is always larger than the value of y. And we construct the model function and the parameters such that their derivative would be a vector, the value of x concatenated by 1, multiplied by an indicator function that will zero this whole thing out if the sample does not match the given prefix. So basically, the value of 2 plus y is used to extract the value of y, and the x is extracting x, and the last one and the indicator function are used to count the number of matching samples. So the outcome of each DFS step depends on the last item of this gradient vector, where if that would be 0, then we will understand that we're in the no matching sample case, and we will terminate this path. If that value will be lower than 4 over s, we will understand that we're in the case where a single sample matches the prefix, and we can extract this sample. And if it's larger than this value, then we will understand that there are multiple samples that match the prefix, and we will recursively invoke the exploration on extended versions. So let's see why this is correct. So denote by SZ the subset of the samples that match a given prefix. If we're in the case where no sample matches the prefix, then it means that this is just an empty set, and correspondingly, the gradient vector will just be a vector of all zeros, and the last item will also be 0, and this is exactly the first condition that we just had. If we have a single matching sample, then the gradient vector would be 1 over s, where s is the size of the sample set, multiplied by 2 plus y, multiplied by x1, and specifically, the last item of this vector would be 2 plus y over s, and since y is binary, then this will be always lower than 4 over s, which is exactly our second condition. In the last case, where we have multiple matches, then without loss of generality, let's assume that we have 2 matching samples. So here, the gradient vector would be the summation of the gradient vectors for each one of those samples. And specifically, the last item would be 2 plus y1 plus 2 plus y2 over s, and this will obviously always be larger than 4 over s, which was our third condition. So here we showed how we can construct our gradient queries such that using a DFS-based exploration, we were able to extract all of the samples, and then we can internally run the computation that was performed by the sample-based adversary. Moving on to our next result is a statistical simulation using fully parallelizable gradient queries. So the problem with the DFS-based exploration is that it is sequential and we cannot make it parallel. So that it is inapplicable to parallelizable cryptanalysis. So we wanted to refine this simulation so that it can now be fully parallelizable. How do we do this? So the idea would be to randomize each iteration using a pairwise independent hash function. So basically, in each iteration, instead of going over all possible prefixes, we will guess the output of some hash function. This allows us to issue all gradient queries at the same time, but this will also have to come at the cost of a statistical simulation and not a perfect simulation. Our last result is a statistical simulation using gradient descent. So both of the previous results that I've just showed are applying to the general gradient-based adversary that can issue arbitrary queries and so on. But as I mentioned in the beginning, the gradient descent adversary follows a particular algorithm. Namely, it means that it can only issue non-adaptive queries that depend on the previous queries that we already issued. So how do we refine our simulation to also adapt to this class of adversary? Then what we do is we encode all of the guesses that we will be making throughout the iterations in advance in the parameters, such that in each iteration, we only use a subset of those parameters, and then it's exactly the same as the fully parallelizable setting. This will also have to come at the cost of a slightly less efficient simulation, since now the size of the parameters are multiplied by a factor of 2, where t is the number of parameters, and this has an effect over the running time. To conclude, in our work, we initiated the exploration of the theory behind ML-based cryptanalysis. We introduced a unifying framework that captures both classical sample-based adversaries and gradient-based adversaries. And we used that to establish a general feasibility result that stated that any sample-based adversary can be simulated by a gradient-based adversary. So going back to our initial question, whether these class of adversaries are inherently limited, then our answer to this would be no. Thank you very much.
Thank you. We have time for a couple of questions. Then I've got one.
Okay.
So you're saying that ML-based cryptanalytic methods are not inherently limited.
Mhm.
Do we have any sort of evidence that natural ML algorithms are doing anything of the type of thing that you're describing?
So it's an interesting question. So our constructions are not like the vanilla ML kind of constructions.
Right.
And it's an interesting open question that we actually want to continue exploring using our framework to see what happens and to what extent will these things hold and what will be the trade-off once we use more traditional constructions. But yes, it's a very interesting question.
Thanks.
Mm.
Thanks, everyone.
Thank you.
All right. Our next talk is Crypt Attack Tester, High Assurance Attack Analysis by Dan Bernstein and Tung Cho, and Tung is going to be giving the talk.
Okay, can you all hear me? Okay. So today I'm going to talk about Crypt Attack Tester, and this is a joint work with Daniel Bernstein. So first of all, what's our motivation? So basically, we want to compare efficiency of attacks, and this is what people are doing all the time. So what was the problem? So the problem is that well, people are often talk about different cost models, and sometimes it's not immediately obvious that's what the difference is. Like, for example, you may see a paper talk about the cost is considered as the number well, few operations, while the other is talking about bit operations maybe, but then they use just costs in their tables. You don't see immediately what's the difference. And sometimes even worse, the cost model might not be well defined, actually. And well, even if the cost model is well defined, well, you must admit that sometimes people can make mistakes, well, they can make errors, or they might want to simplify things, so they just do estimations. Yeah. So in our framework, the CAT framework, what we want to do is like we try to solve these issues by having a clear and well-defined cost model plus testing. Okay, so concept is actually very simple. There's nothing very involved. Yeah. And yeah, another thing is that well, I didn't define efficiency, but in CAT, efficiency is considered to be evaluated by two factors: cost and success probability. Okay, so let me start with the cost model. So in the CAT framework, each attack is essentially just a circuit. Okay, and what's a circuit? Well, it's a fixed sequence of operations. Okay, and then the next question is what's an operation? Well, an operation is well, it's just some operation that acts on up to 2 bits. Okay, so you can apply some function to up to 2 bits and then store it into the variable xk. Yeah, that's what the case operation what it does. Yeah. And yeah, F can be, well, essentially anything that maps from L bits to just 1 bit. Yeah. And one thing I didn't put in this slide is, well, the first variables, x1 to, for example, xn. Well, these are for the input, yeah, as you can probably imagine. And the cost is just, well, the number of operations where L is 2 or L is 1, but it's doing the not operation. Okay, so this is our definition of costs. Okay, and then for anyone who want to claim the efficiency of their algorithms, they need to write these 3 pieces of code. So the first one is a piece of code that defines a family of attack circuits. What I mean by family is that you can have parameters for the circuit. Now, this is natural because your problem can scale. And then if you run this A, it generates the exact cost, and we're not doing any overestimation or underestimation. And you can also try to measure the success probability by, well, running A many times. And the second piece is C. Well, this is a piece of code that should predict the cost of A. Now, and the difference is that, well, we should generate the cost very quickly, even when A is not able to generate the cost because it's probably too slow. Yeah, and then how do we gain confidence in C? Well, we compare C's output with A's output by running many experiments. And yeah, of course, here, because A is slow, so you cannot do very large experiments, but we can at least do many small experiments. And also, we have this P, that's for predicting the success probability. And similarly, it should generate the output quickly. And then we gain confidence by comparing P's output with, well, the measurement results of running A. Okay, how do we count the bit operations in 8 automatically? Well, basically, when you're writing this A, then everything need to build upon this class bit. Yeah. So this is how you define your variables, xi's. And yeah, please notice that here the bit in B, it's private. So when people are writing coding for A, you cannot really touch these variables. And then you can make use of the member functions and the operators. These are the bit operations you are allowed to do. And then as you see, you can this class will automatically count the number of operations for you. And here's a very simple example. So you can write half adder and full adder, or just need to define the corresponding bit operations. You don't need to take care about the counting part. Of course, you can do something more complicated, like this function is essentially adding two integers and then taking one bit as the carrying bit. Okay, and this can be very, very complicated. Like you can, if you want, you can specify circuit in the CPU. Okay. And probably the biggest thing you need to remember about this model is that when operations are expensive, and this is basically because in real world it's expensive. Okay, so consider for example, this example of that you want to read from 8 bits by using this index I. And the best you can do is essentially like this picture. As you can see, the number of gates is going to be at least linear to the number of bits you're accessing. Okay. And yeah, if you think about the real world RAM, then probably you're thinking about something that has a fixed size. But in our model, it depends on like how many bits you want to do random access. So for each time you want to do this kind of access, it can be different. Okay. Okay. Yeah, here's a more interesting part. So we actually make use of the CAT framework to implement some attacks. So the first one is a brute force attack against AES 128. And our setting is that we have two plain text ciphertext pairs, and the goal is to find the key. And yeah, according to our prediction, the cost is like 23141, and then success probability is 0.5. If you know about this definition of the security categories, then you probably know that the smallest category has 2 to the 143 classical gates. So you might consider that, okay, these two roughly match. Yeah, but the thing I want to mention is that, actually this our implementation is very naive, and you can probably improve it a little bit. And another thing is that if you consider the what one is called a gate count model, which seems to be a favorite model, then in this model you can make use of very cheap RAM accesses, and it's almost for free. And you can it's not so surprising that you can actually reduce the cost by making use of this RAM accesses. And we have some argument in the paper that you can check. And we also have actually more complicated attacks like information set decoding algorithms against syndrome decoding problem. And yeah, what we implemented is it covers several many variants like Leon Stern. Well, probably you have heard of this famous ISD algorithms. And yeah, one thing we do is like we try to merge algorithms with the same numbers of levels of collision search. So we end up with ISD0, ISD1, and ISD2. And yeah, we have as I mentioned, it's more complicated. So there are many parameters and many low-level optimizations. And for details, you can check the deepened version of our paper, because unfortunately, we're not able to put everything in the crypto paper. Yeah, I would like to cover a bit about or some optimization we do for ISD algorithms for how we do collision search. If you check previous papers, then most of the time you will see that people are doing RAND operations to find collisions. Well, this is very convenient for those papers because for them, RAND access are very cheap. Maybe sometimes it's taking just constant time. But for us, it's quite expensive. Well, actually, it's more expensive for real-world circuits, actually. So in order to this expensive operations, what we do is like in order to find collisions between two lists, L1 and L2, we first sort all the elements in this two lists, and then we use a sorting network to sort the combined list. And then we check all the pairs of the form Li and Li plus D, where D is not more than this parameter Wi. And yeah, as you can see, we might actually miss some collisions because, well, Wi might not be big enough, right? So yeah, this is something that we need to handle. Yeah. And we pick a specific sorting network that's a Kuhn's merge exchange algorithm, which is taking n log square and compare and swap operations. Okay, I still have time. And another thing that we might try to make use of queues, which is, okay, maybe it's not so obvious now why we're using this, but essentially, if you consider the collisions we found, then usually we want to do some, we want to process them later in some way. And the tricky thing is that you don't really know when we will get a collision. Yeah. So the naive thing is to just store all the collision you get in a large piece of memory or a collection of variables. And in order to do this, well, because you don't know when you get collisions, well, it seems that you always need to have some kind of random access. And that's expensive, as I mentioned. So what we do is that we try to push collisions into a queue of QU elements. So here, QU, again, is a variable we can change. And then what we do is that we periodically process all the elements in the queue. And then, well, after we process them, we clear the queue. Okay. And we have another parameter, PE, for that, for the period. So after PE pairs are checked, we'll do this clear operation. Okay. Yeah, and again, so here we might lose some collisions. And now this is because for all the collisions all the pairs we check, if it leads to collision, they will get pushed into the queue. This is for sure. But the problem is that if the queue is full and then you still want to push things into it, then okay, something might get kicked out from the queue before you actually process the queue. Okay, so this again, this needs to be considered by P. Okay, and one optimization we do is that in order to avoid this kind of situation, we try to randomize the order of the pairs we're checking. Okay, this is essentially my last slide. So yeah, we have some numbers generated by CAT. For example, we have like necklace 1284. This is an instance that got broken in one I think Eurocrypt 2022 paper. Yeah, as you see, it has around 71 bit of security. And then for the remaining columns, we're showing the parameter sets for classic McLeese. Okay, so this is essentially my talk, and you can check our website for the source code. And as I mentioned, there are something that we put into ePrint version, but we were not able to put in crypto version. So yeah, if you're interested, please also check those details. So yeah, that's all for my talk. Thank you for listening.
We have time for questions.
Question, yes. Can you explain why you chose circuit complexity as your basic measure? Because it's wildly incompatible with software complexity or the complexity we actually use in the real world.
So that maybe you can state. I mean, so what's your concern here? Like, what do you think?
Well,
What's the difference
Your
between?
memory accesses are far more expensive, and you do a lot of work to try and avoid that for one particular use of memory. If I have an if statement in a circuit, I have to evaluate the whole if statement every time. In software, I only do it very rarely. So there's lots of things that when you move to circuit, unless you build your circuit just to build a CPU, in which case, why bother? That circuits end up doing a whole lot more work than our practical implementation would have to do.
Well, I mean, maybe this is related to one of my slides, well, if you want, you can specify a circuit in a CPU, and then you can try to implement your attack in a way that's more like software, if you want to consider this.
Yeah,
And yeah, this is possible. And yeah, I mean, for many people, many people who are familiar with thinking in a software way, but they probably ignore that inside your CPU and inside the memory of your CPU, the CPU is doing lots of things in one cycle. And that's not something you can just say, oh, it's because it's taking one cycle, so it's just one gate. Okay, so if you think about this, then maybe this model will be more reasonable for you. But another thing I want to mention is that I don't want to limit the possibility for other people to define other models. For example, if you really feel that there's something that you are not satisfied with this, then okay, please try to define a well-defined model. I'm totally fine with that. But what I want to say is that I think our model is very simple, and because of the simplicity, there are many advantages. And I hope in the future, when people are defining new models, they can try to keep these advantages. Okay, and then yeah.
Basically, write a crypto 2025 papers.
Hi, thanks for the talk. I was wondering, I'm always curious about very parallel attacks like Van Oscar-Wiener's parallel collision. And often what I worry about, because I have nothing better to think about, is how like the orchestrator handles all of these. I was wondering if you in CAD, you can account for, say, having parallel processes going on and one finishing much earlier than the other, or like having like a network card that has to get like 264 points being sent to it.
Yeah, I have to say this is something that's not considered in our model so far. Well, our model doesn't consider many things. This is just one thing. And yeah, so far I don't really know how to what's a good way to go toward this direction. But yeah, maybe we need another better model, maybe. And then from there, I think the first thing is probably try to define what's the thing you want to measure or you want to evaluate, like for example, parallelism. What does parallelism mean? Okay, then yeah, once we have a clear definition, I think it will be more obvious about like what we should do or what we should change to fit your need. Yeah.
Thanks.
Thank you.
Crypto 2026 paper.
So am I mistaken in understanding that this is basically an unrolled circuit? So it's not the size of the circuit, because you are recounting every gate when you're reusing it. So it's essentially like a one-bit computer model where you have a list of instructions and
your understanding is correct. Yeah.
yeah. So in hardware, for memory, you don't have to do a full MUX, a tree like that. So there's it's basically a matrix that you pick up in there, and of course it's it's a circuit, so things go back in there. And for example, energy consumption, it depends only on switching power quite often. So static power is much less. So I mean, one could think that it might be related to energy, but not really, because it's not switching power. And because of the parallelism and the memory concern, it doesn't exactly match with the like ball clock complexity of these algorithms. So yeah, I think it's a little limited when we're yeah.
Yeah, so sorry, I didn't catch everything, but I remember you said about energy. So
Energy is kind of every time you switch a state, basically that is rough estimate for switching energy. So a CMOS circuit would have static power and switching power, and that would be the energy measure. So this is perhaps related to that, but because the memory is so different here than in real life, it's not quite that.
yeah, I haven't really thought about how to model energy, but yeah.
Sampling is a good.
Yeah,
All right.
as I
Thank you.
mentioned,
Thank
maybe
you.
we can try to figure out how to modify the model and then try to fit your unique. Yeah, thank
I
you.
was trying to map it into like measurements.
Thank you, Tom, and thanks everybody for the questions. We'll go on to the next class. Our next talk is not just regular decoding, asymptotics and improvements of regular syndrome decoding attacks. The paper is by Andre Essa and Paolo Santini, and Paolo is giving the talk.
Yeah, but I just broke the microphone, so
Did you break something?
yeah. Cryptanalysis. Can you hear me like this? Okay,
Yeah,
perfect.
awesome.
Okay. Let's see if this is working. Yeah. Okay, so good morning, everyone. I'm Paolo Santini, and today I'm presenting this paper, which is a joint work with Andre Esser, and the paper is about cryptanalysis of the regular syndrome decoding problem. Okay, so the problem is very similar to the syndrome decoding problem. We just saw something about it in the previous talk, but here the key definition is that of regularity. So we have this regular vector, which we define as a vector, which can be seen as a concatenation of blocks. All of these blocks have the same length and Hamming weight equal to 1. So if we have Hamming weight W, we have exactly W blocks. So that's the key ingredient. And then we can define the regular syndrome decoding problem, where the input are a parity check matrix H. You can think of H as a rectangular matrix, R rows and N columns. S is the syndrome. The final input is W, the weight, and then we want to find a solution. So a vector E such that H times E is equal to S, and E as weight W, and it is regular. The problem has been introduced in 2003 for the proposal of a Shortly candidate, and since then it has been used for the construction of many cryptographic schemes, and in particular in the last years, the problem has been introduced to build post-quantum signature schemes. Digital signatures, obviously. So in many of these schemes, we are in a setting which we call randomized setting, which I will define. And this is the setting we study in the paper. So essentially, we sample a uniformly random parity check matrix H, and then we guarantee that we have at least one solution. And we do this by first picking a regular vector, a random vector, and then we compute S as the product between H and E. In this setting, we can estimate the average number of solutions. We have this formula here. And in particular, we can define conditions that guarantee that on average, we have a unique solution. This is what we call the uniqueness bound, and it is the analog of the Gilbert-Vashamov bound for the regular syndrome, for the standard syndrome decoding. And the formulation you see in the slide is obtained assuming that the number of rows in the parity check matrix is linear in N, where kappa is called code rate, and also we assume that W is linear in N. And so essentially, if you fix your code rate kappa, then you can use this bound to find the largest weight, guaranteeing a unique solution on average. Now, speaking about attacks to the problem, obviously we should start from information set decoding. Again, we just saw something about ISD in the previous talk. ISD is the best solver for the syndrome decoding problem, so it makes sense that we consider how ISD performs on the regular syndrome decoding problem. But actually, there are papers in which the algorithm has been used to attack the problem. However, in the end, the authors concluded that basically considering regularity does not give you advantages. So the complexity of ISD on the regular syndrome decoding is essentially the same as ISD on the standard syndrome decoding problem. However, in the last year, in Europe 2023, two papers appeared, and in these two papers, the authors consider new attacks to the problem. In the first paper, by Biot and Garden, the authors study algebraic-based solvers, and they show that essentially these solvers are faster than many of existing solvers, so they are able to cryptanalyze many schemes. And then in this paper, which I will refer to as the CCJ paper, the authors propose a single scheme based on ISD, and also new solvers, and moreover, they start a classification of the hardness of the problem in the sense that they compare SD with RSD, using the number of solutions as a way to understand which problem is harder and which one is easier. So we saw this paper, and then we started working in the problem. We wanted to understand more, to study attacks, etc. So now I can summarize the contributions of our paper, and in particular, as a first contribution, we propose regular ISD algorithms, essentially new algorithms to solve the problem. We have 4 new algorithms, and we show that these algorithms are the fastest solvers for worst case ISD instances, and also for many practical cases, we obtain the best attacks. So essentially, for many schemes, we are able to decrease the security level. Then, using also the cost of these algorithms, we continue the classification of the problem, and in particular, again, we compare syndrome decoding and regular syndrome decoding, and we show, first of all, that there are easy regimes, so cases in which RSD can be solved in polynomial time. And also, perhaps, this goes against common intuition, we show that the regular syndrome decoding is actually harder than syndrome decoding in some cases. And in particular, if we consider the worst case instances, this new problem is harder than the standard one. Finally, as a third contribution, we have the artifact, which is associated with the paper. In the artifact, you can find all the code we have used, so essentially the estimator for the cost of algorithms. We have also proof of concept implementations for the simplest algorithms. That's it. Now, let's see some details. I will not have the time to show you all details of our algorithms. I just want to show you what we can do in the regular setting. So we have essentially 2 main techniques, and the first one corresponds to adding extra equations. This is not new. This has already been used in these 2 papers I already mentioned. And basically, the idea is that since you know that the solution is regular, you can append extra equations. So you're making your problem easier. And the equations, obviously, we are speaking about linear equations. Essentially, you get these new relations by considering that if you sum all the elements in a block, the sum is equal to 1. So you append these W equations. You also update the syndrome. And in terms of code in theory, you're making the problem easier because you are decreasing the code dimension, and so you are decreasing the code rate. Then the second key ingredient in all our algorithms is given by regular permutations. Essentially, if you are familiar with ISD algorithms, you know that every ISD algorithm starts by sampling a random permutation. This is necessary to shuffle the elements of the solution, hoping that you get some particular weight distribution, etc. However, if we start from a regular vector and we sample a random permutation, then obviously, with large probability, we destroy regularity. So in our algorithms, we wanted to use something, some class of permutations that provide a nice interaction with regular vectors. And the solution we found corresponds to what we call regular permutations. So this is a class of permutations. We have this index B. And essentially, the permutation works as you can see in the slide. For every block, you select at random V coordinates, and then you move these V coordinates to the right and the remaining ones to the left. So if you start from a vector, having W blocks, the result is W blocks again on the left and W blocks on the right. And so, I mean, basically the idea is that using this type of permutations, you can essentially improve ISD because somehow you preserve regularity. So when you do enumeration, etc., you can make use of this property to speed up the procedure. I will show you some quick details about the simplest algorithm. We have the permutation-based regular ISD, which is the adaptation of Prange's ISD. Really, the algorithm just uses extra equations, these rows you can see in gray, and then samples regular permutations. The algorithm succeeds when on the, so you see, with the regular permutation, we shuffle the coordinates of the solution we are searching for. And if we are lucky, then in the rightmost part, we have only zeros. And in this case, we can detect this using basically systematic form. So this is really like Prange. You sample regular permutations, you do systematic form, you check the syndrome, the new syndrome. If this is not valid, you start again. That's the algorithm. In particular, differently from standard Prange, in this case, we construct the information set by sampling V coordinates from each block. That's what the regular permutation does. And here I must mention some, this is important, an important technical issue, because obviously we cannot guarantee that V is an integer. So in this case, the algorithm gets a bit different, because obviously we must sample less than V from some blocks, more than V from the other blocks, etc. If you take this into account, then computations get very boring and they change, but we can show, and actually we show this in the paper, that the impact on complexity is very moderate. Yeah. So this was for the simplest ISD algorithm, but then in the paper we have also advanced ISD algorithms, where essentially we translate advanced ISDs. So we have Stern ISD, BJMM, and Mayotzerov, and for all of these algorithms, we have the regular counterpart. Again, I cannot show you details. I will just tell you that these algorithms turn out to be the fastest ones if we consider worst case ISD instances. This is a comparison with the fastest algorithm from the CCJ paper. And moreover, if we consider schemes based on ISD, in many cases, we are able to decrease the security level because our attacks turn out to be the fastest attacks out there. This is a selection of instances from the paper. From our paper. In the paper, we have many more instances and schemes. Yeah. So I'm going to conclude my talk by telling you something about the classification of the hardness. Here, by classification, we mean we really want to understand what we can do with this problem. In the sense, we want to compare with the standard syndrome decoding, assuming that we are using the same code parameters. So we have the same code length, the same code rate, kappa, and also the same weight. Yeah, this is the relative weight omega. And so we really want to understand whether this problem can be harder than syndrome decoding or vice versa. I mean, the main intuition is that regular syndrome decoding should be easier. We have this extra structure. We can somehow use it to speed up attacks. So we expect the problem to be harder. However, we will see that this may not be the case. Let's see how much. Okay, I have a lot of time. Okay, so everything will happen in this figure here. Again, on the x-axis, we have the relative weight, so essentially the weight, while here 1 minus kappa, so the number of parity check equations. We can define these three regions which depend on the bounds. So in each of these regions, the problems behave differently. For instance, in the blue region, the solution to syndrome decoding is unique, and also the one to the ISD is unique, while here SD has multiple solutions, while ISD has only one solution on average. So first of all, we see in this blue region, syndrome decoding is harder. This happens because both problems have the same number of solutions, one. However, for the regular syndrome decoding, we can make use of regularity to speed up attacks. And so if we consider the cost of regular ISD algorithms, in this case, ISD is easier. Then we can also identify a polynomial regime. And this regime is associated to the existence of exponentially many solutions. And both problems in this zones have multiple solutions. And in this case, if we consider the cost of existing algorithms, they run in polynomial time. And this is very easy to see. Since we have a lot of solutions and we're satisfied with any of these solutions, we sample a random permutation, and with extremely large probability, this permutation will give us a good solution. That's it. So we just do one iteration, and that's it. Then we have also this regime in which RSD is polynomial, and this is something which is specific to the regular syndrome decoding. And the existence of this regime is due to the fact that we can append equations, extra equations, due to regularity. And if the number of equations is too large, which means if the weight is too large, then the pi check matrix becomes a square matrix. So the number of equations is larger than the number of unknowns. So basically, you don't guess anymore, you just solve a linear system. That's it. Okay, so now we have to understand what will happen here. And we can divide this region into two parts. We see that if we are close to the GV bound, then syndrome decoding remains harder. And this happens because essentially the number of solutions in this white region is not, I mean, it's larger than one, but still not super large. So syndrome decoding remains harder. However, if from the GV bound we move, so we get far from the GV bound, essentially, we see that here, regular syndrome decoding has only one solution. Syndrome decoding has a lot of solutions, exponentially many solutions. So syndrome decoding becomes easier, and regular syndrome decoding becomes harder. And this is perhaps, I mean, we were not expecting this, but this is what happens if you take into account the cost of known algorithms. And in particular, we see that looking, if we focus on worst case RSD instances, once we fix the code rate, then we have this formula to select the hardest instances. And again, this is an important difference with respect to the syndrome decoding problem, because we know that in that case, you always select hardest instances using the GV bound. In this case, in some cases, the uniqueness bound does not correspond to the hardest RSD instance. And again, this is due to the fact that we can append extra equations. So if the weight is too large, then we append too many equations and we make the problem easier. So in some cases, the worst case instances are those where the weight is a bit smaller than the one resulting from the uniqueness bound. Okay, finally, if we focus on worst case instances, we see that RSD is actually harder. And again, the high level intuition for this fact comes from the fact that basically you can, I mean, when you add regularity, essentially you are reducing the number of solutions with respect to the standard syndrome decoding. So because of regularity, you can select a larger weight and still guarantee a unique solution. We know that all ISD algorithms in practice work by guessing positions of zeros. So if we increase the weight, we make this guessing phase harder. And so that's the level intuition behind this behavior. Okay, so I'm going to conclude the talk by saying that in this talk, we have introduced regular ISD algorithms, which essentially are adaptations of ISD algorithms from the standard syndrome decoding setting to a regular setting. We studied these algorithms in terms of time complexities, space complexities, etc. And we see that regular ISD algorithms turn out to be the best solvers for the regular syndrome decoding problem in many cases. We have also used the cost of these algorithms to start to continue the classification of on the hardness of RSD, and in particular we compared with syndrome decoding, and we found that in practice this new problem can actually be harder than syndrome decoding. And yeah, I mean, if you want to see full details, you can find them in the paper. And if you have questions, I'm here. So thanks a lot for the attention.
Questions for Paolo?
Any implications on the schemes that are proposed that we're relying on this assumption? Is anything broken? Is anything just sort of needing better parameters? From your attacks, what are the implications on the schemes that are relying on RSD? Is it that they need to change their parameters, or is it that it's too asymptotic to have concrete?
No, so for some of these schemes, actually, parameters shall be changed. And I want to show you the table about this. Yeah, so yeah, in the paper, actually, we try to find, I wouldn't say all, but a lot of schemes based on RSD.
Right.
And for all of these schemes, we computed the complexity of our attacks. In some cases, we found that our attack has a time complexity which is below the claim security level.
Okay.
So yeah, in these cases, I guess you need to change parameters. Yeah. But there are also cases where our attack is not the best attack. And this depends, I guess, on how you choose parameters, because in some of these instances, for instance, you have a very small code rate. So in this case, something different happens. It also depends on the relative weight, if it is linear, enhanced, sublinear, etc. So yeah.
That makes sense. Thank you. Thanks, Paolo.
Thank you. Is it on? Yeah. Okay.
All right, our next talk wins the cleverest title in the session award. Full Leakage, Breaking Fulika by Learning Attacks by Felicitas Erman, Vessel van Woerden, and Felicitas is giving the talk.
Okay, it's working. Thank you so much. I'm very excited to be here to present our work to you. And I would like to start by giving you some motivation on why this is interesting. So first of all, Fulika is a code-based signature scheme that uses quasi-cyclic codes in the Lie metric. So not in the Hamming metric that most coding theorists are very familiar with, but in this different metric. It was presented at CB Crypto 2023, which was affiliated to Eurocrypt. And it was also submitted to NIST's call for additional post-quantum signatures. What we do in our paper is we propose 3 different attacks on the signature scheme. In fact, we have 2 classical attacks. One actually uses very little signatures and reduces the security levels. And then we have one learning attack that is a full break, but uses a bit more signatures. Then we also have a quantum attack, which uses some specific structure, but because of the limited amount of time, I will focus on the 2 attacks in the upper row here. The cool thing about the paper is that the signature scheme is actually code-based, but we actually broke it by using lattice-based techniques to do that. And this, as we will see, is due to the fact that the Lie metric is actually pretty close to the L2 norm. So this is the outline of my talk. I will first try to give you an overview of how Fulika actually works and how codes and lattices are related to each other. Then I will show you the leaked sublattice attack, which gave a reduced security level. And then finally, I will focus on the learning attack, which is a full break. So first of all, let me say that we use the symmetric representation for the finite field FP. So we represent elements in minus p minus 1/2 until up to p minus 1/2. And then if we look at the definition of codes and lattices, we can already see that they are quite similar. So on the left, we have Lie metric codes, which are defined by a full rank generator matrix over FP. And to obtain code words, I would just multiply a length k vector of FP to G from the left. Similar, if I want to define lattices, I can do the same. I can use a full rank basis, but this basis is over R this time. And the only thing I allow are Z combinations, so integer combinations. In terms of metric that we use, as I already said, we use the Lie weight here, not the Hamming weight. And the difference is that we don't only count the number of non-zero entries, but rather we sum up the absolute value of the entries of a vector. And on the right-hand side, we use the typical Euclidean norm that we are all familiar with. So here's a quick picture of what actually balls of a certain radius look like. And you can see in the Lie metric, you get this diamond shape, whereas in the Euclidean domain, we get a circle. Of course, this is not the same thing, but if you now imagine you put these two over each other, you can already see that there's quite some overlap happening there. And this is more or less what we will use because these metrics are closer to each other than one might think at the first glance. So Felica is a hash and sign signature scheme. So let me just recap quickly how this works. So I start with a message M, then I hash it to a target T. There will just be lines somewhere randomly. And the signature is then a code word that is close to my target. So as a verifier, if I want to check if a signature is valid, what I can do is I can simply check if S lies in my code and if the Lie weight of S minus T is bounded by a certain predefined threshold. In fact, you can notice that as a signer, I really need a good representation of my code because if I have a target, I need to be able to decode to a closed code word. But if I'm on the other hand a verifier, I don't need that. I simply need any representation of the code to be able to check if the signature is a valid code word. And now let me talk about the details about Felica. So the key generation works as follows. We generate a secret vector G, and it has two halves, A and B. And A and B are drawn uniformly at random from the set of all length K vectors with a fixed Lie weight W key. In fact, W key is a preset parameter, and it is pretty small. So these vectors are short in the Lie metric. The secret key itself is then a matrix consisting of two circulant blocks, A and B. And these circulant blocks are circulant, so they use A and B and just always shift by one entry. For the rest of the talk, I will also use the notation G1 up to GK to denote these quasi-circulant shifts of the secret vector G. As a public key, I simply use the systematic form of the secret key. So I get the identity matrix and then A to the minus 1 times B. Okay, so far so good. So what do we want to do? Well, we want to find the secret vector G, or any of its shifts, because, I mean, it doesn't matter in which order I put the rows of G. And in fact, if you look at the definition of GPub, I can even only be fine with finding A because I can compute B from that. So I said we would do that using lattice techniques. So the first thing we should consider is how do we get a lattice out of our code? Let me start here from a code. And the simplest thing I can do is I just copy it. And I copy it as long as it fits into my space, so infinitely often. And what I get is this lattice from construction A, which includes all vectors V and Z to the N, such that V mod P is in my code. I can also represent that differently, because basically I take the main square, and then I shift it by P in the first dimension, I shift it by P in the second dimension, and then I get all possible shifts. So I can write it as C plus P times Z to the N. And in fact, this lattice is a rank N lattice, and I can explicitly write down a basis for it. In fact, I get the public key in the first row in green, and then I have to add P times the identity to be able to recreate all the shifts that I did. Okay, so far so good. I told you earlier that the secret vector is actually short. So what do lattice people do all the time? They find short vectors. We can do that here. I don't want to go into details, so we use some black box lattice techniques, and we can find a short vector in the complexity in the order of 2 to the 0.292 n. In fact, the Felica team already considered that, but ISD attacks are more efficient, and therefore this attack was not really relevant for their security estimates. And now one important observation, if I really just look in the central square, I'm back to my code basically. And there, the Lie metric is exactly the L1 norm. And L1 and L2 are very similar you can compute bounds in both directions. So we have seen how we can construct a lattice from a code. And now the question is, how can we make this more efficient to actually break the system? And our approach is to find a sublattice that has a lower rank and therefore a lower attack complexity. So to do that, we need to understand how Fulica generates signatures. And then we will find out what kind of structural properties it has to see which sublattice might be suitable for our attack. So let's start with a message hash C. And then we compute a signature in a two-step model. So first we start with a simple signing, and then we do a concentration step. And the simple signing first just chooses V as a code word that is close to my hash. So the typical thing to do in the hash and sign paradigm. In fact, if you want to see the formula, here it is. So V is chosen as the product of X times GSEC, where X is a vector whose entries are computed basically more or less as the scalar product of your message hash with the signs of your secret vectors. There's also a constant, but we don't really worry about this in this talk. And the main goal of the concentration step is that actually V should be adapted such that its Lie weight and also the number of sign matches with the message hash C lie in prescribed intervals. And how they do that is they iteratively try to add the secret vectors G1 up to GK, so the shifts of that. And then they recheck if it got better or worse, and they just continue the process until the signature actually fulfills their properties. One important thing to note here is that the entries of X and GSEC are rather small, because, I mean, the X's are some small constant S over 2 times the product, the scalar product of a vector that is in plus minus 1 and a vector that is in plus minus 1 and 0. So there's not so much that can happen. And GSEC also, as I told you earlier, was sampled from this very low Lie weight sphere, and therefore the entries cannot be super large. So the entries of these two things are rather small, but the P they chose for all parameter sets is 65,565, and thus pretty large. In fact, what happens is that in this computation of signatures, no wrapping modulo P takes place, and I can instead just do it all over Z. I don't have to worry about finite field operations. What does that mean? That means that all signatures actually lie in this central square that I showed you earlier. And in fact, there the Lie metric coincides with the L1 norm. So now it's time to exploit that fact. Let's go back to our lattice that we had before. This is LA, and the basis that we saw earlier. If we don't have to do all the computations over FP, but we can do them over Z, we can just use this basis instead, and we know that the secret vector is in the lattice. And since we don't really use this modulo P anyway, we can get rid of the lower rows, and we're just left with a sublattice whose basis is our secret generation matrix GSEC. In fact, this thing has rank n half. So we halved the exponent in the complexity by just using the same black box lattice techniques. And there is even more to that, namely the secret vectors, and it's like their circle and shifts. They are unusually short. So they are shorter than what you would expect in a lattice of that parameter set. And therefore, you can even reduce the attack complexity more, and you get a complexity in the order of 2 to the 0.292 n over 4. And then just a quick side remark. Since this sublattice actually has additional structure, we can use that to then go to some quantum algorithms and get a quantum polynomial time attack. But I don't go into details today. If you're interested, it's all in the paper. And there's one thing that I didn't tell you. So Yeah, we have this sublattice, but we need a basis because otherwise, how should we use any basis reduction if we don't have a basis? But in fact, we can show that if you just use signatures and extract a set of generating vectors from them, the probability that you actually span the whole lattice is pretty high, pretty quickly. So you don't need a lot of signatures to generate L sub, and then you have a basis, and then you can continue with basis reduction and recover the secret vector. So what does this attack mean to Fulica? Here is a table of updated security levels. And we see that for security level 1, it drops from 160 bits to 111. For level 3, from 224 to 155. And for security level 5, from 288 to 199. This means in all cases, the NIST standards are not met anymore, and the system is broken. But, you know, why not fully break a system if you can? So we also derived another attack, which is a learning attack. And in this case, the main idea is that you get some sort of leakage from every signature that you have. And so you collect a certain amount of signatures and you try to extract this bias that you get. And then you try to exploit it to recover your secret vector. So what is the bias in terms of Fulica? Let's go back to this signing step. So we had first like a simple signing step, and then we had the concentration procedure. In the concentration procedure, Fulica tries to add and subtract these GIs to the signature to make it, in their sense, better. But the problem is that this process is not randomized. So in fact, they always start by trying to add G1, then they try to subtract G1, they try to add G2, they try to subtract G2, and so on and so forth. And this actually implies that here in dimension 2, we can see a bias. So we would expect a circle, but in fact, what we get is this ellipse that really is in the correct dimension, directions for our secret vectors. If we actually observe the average of the xi square, where the x was the vector that I used to create the signature, so v equals x times g sec, then we can see here that we have a bias there. So they are increasing with growing index. In fact, as I already said, this is because the loop is not randomized. And we try to recreate it for a randomized loop, and there we don't get this anymore. So this is a super simple fix for this attack, but most likely there is a similar attack that doesn't even abuse that, but we haven't dig deeper into that. So how can we exploit it? We start by collecting signatures, capital N signatures, and we focus on the first half of each of the signatures. So we focus on WI, which is then the product of xi times a, which was the circular part for the first half of our secret vector. Then we can compute the average of WTW by just summing overall WIT WI and averaging that out. And this is an approximation of the expectancy of WTW. So then we can write it like that. And we can even write E of XTX as a sum of the diagonal matrix. So we just put all the diagonal entries there that it has, and all the off diagonals are moved to R. Okay. So here's again the same equation. But now we write ATDA plus E. And in this error matrix, we collect all the errors that happen on the way. So basically, the approximation error that happened when we had like our N signatures, and also all the off-diagonal elements of the expected value of XTX. So the question is, if we have that, how do we recover? And in the case E equals 0, of course, no error really happened. That's the simple case. And we can provably recover A here, because A is circulant, which we can abuse. And also D has this increasing shape, like the diagonal elements of D are increasing. If E is not 0, then we recover A with high probability by just approximating it first and then turning the guess into an exact solution. But I can't go into details here. You can read it up. Yeah, and here you can just see how quickly this converges to the exact solution from the guess. And here is a plot of the overall success rate of the learning attack. In fact, that means that 175,000 signatures are enough to fully break all security levels of Fulica. And yeah, I guess that's pretty devastating. So let me conclude. Fulica is broken. I showed you several attacks here, mostly the two in the upper row. And the main problems were that P was too large to have wrapping modulo P, and also the signature leaks some information about the secret GSEC. In the bigger picture, that means, well, that the Lie metric is actually pretty close to the Euclidean norm, and so codes and lattices, especially with respect to the Lie metric, are closer to each other than some people might think. So please, in case you try to work with that, take this into account. And also, if you want to work on the Lie metric, it might be interesting to see if this leakage can be prevented by providing a proof in the GPV style framework. Yeah, and I hope you found this interesting. In case you want to get more details of our work, here's the paper and also the artifact with which you can run the attack on your computer in real time. Thank you.
Questions, anyone?
Hi, thanks for the talk. Could you go back to slide 7?
Wrong direction, sorry. This one.
Yeah, so here you divide by 2 the exponent by mentioning a lattice attack.
Yes.
Is this just like block reduction, like doing BKZ?
We do BKZ, and in fact, here we get the division by 2 because the rank is halved.
And do you do BKZ just assuming the targeting the L2 metric then?
Yeah. Yeah.
Okay, thanks.
Right. Thanks for this, and lunch.